Welcome to lecture 5.6. In this lecture, we're going to introduce cycloalkane rings, angle strain, and the concept of the chair conformation. Now, cycloalkane rings refer to rings made up of sp3 carbons. And very importantly, it's good to remember that sp3 carbons have the ideal bond angle of 109.5 degrees. Now, angle strain can be described as a deviation from that ideal bond angle. Looking at this 3-carbon ring here, or cyclopropane, we can see that despite the ideal bond angle being 109.5, forcing the shape into a triangle is going to necessitate a bond angle of around 60 degrees. So this has a very horrible angle strain and isn't very stable. Of course, it can exist, but we're talking about the stable rings today. Another example of an unstable cyclo ring, or cycloalkane ring, is cyclobutane. Here we can see that this is a little bit better. We're getting closer to that ideal bond angle, but making a square with carbons requires a bond angle of around 90 degrees, which is still lower than 109.5 and suffers from angle strain. Now, the 6-membered cyclohexane ring is quite interesting because if you look at the shape of a hexagon, as we draw it here, I've told you before that flat lines typically indicate that we're talking about the plane of the page. So if all the lines are flat, wouldn't this be a flat ring? Well, if that was the case, the bond angle would be 120, and that does deviate from the 109.5 bond angle. Now, an example of what this ring might look like using a 3D model kit is something like this. We see that from a specific angle, it looks like this ring is a flat hexagon. However, it turns out that the bond angle here is not 120 degrees, but is exactly 109.5. So this ring has no angle strain. Well, how does that make sense? To understand that, we need to take a new perspective of this ring. Taking this same model kit and changing the orientation a bit, we get a molecule that looks more like this. And we can see that from this perspective, these bonds, so each one of these black dots here represents a carbon, you can see that they're indeed not flat. We can see that they move upwards and downwards, allowing for a nice bond angle of approximately 109.5. So how can we draw that? This is the true conformation of the 6-membered ring. Here, we would call this the flat projection. And this can be very useful for multiple reasons, and we'll discuss these reasons later. For one, it's much easier to draw. Another word for this you might see is the Haworth projection, which really just means that we're viewing it from this perspective of a flat ring. Now, this here is the chair configuration. Right? And the chair configuration is the true 3D structure of a cyclohexane ring. To be clear, this is only going to be occurring with cyclohexane. Now, again, a very important part of organic chemistry is taking 2D drawings and understanding what they look like in 3 dimensions. So drawing the chair can be tricky, and in this lecture, I'll show you how to draw it and how to understand its shape a little more. Now, on a 2D piece of paper, the chair configuration is typically drawn like this. You may also see it in a different perspective, something that looks like this. Now, for now, I'll just focus on this first one that I drew. We can see that there are still 1, 2, 3, 4, 5, 6 carbons that make up this ring, but now we get an idea of that 3-dimensional structure that we can see in this image down here with the model kit. So why is it called a chair? This is something that many students get confused by, and there is actually a way to understand this. Now, a few things to notice. First, every carbon seems to alternate the direction of its bonds. So starting from this carbon, we kind of go upwards to this carbon. Carbon 2, let's say. Then we move to carbon 3, and carbon 3 goes downwards, and then upwards again, and then downwards, and then upwards. So we have this alternating pattern. That's one important thing to notice about the chair configuration. Another is that I like to view that we have 4 central atoms. So if we take these 4 atoms, and we draw a little hypothetical dotted line here, it's almost as if these 4 atoms make up a bit of a square. In the 3-dimensional drawing, we would see this as this area here. Now this I would view as the place where you could sit, or the sitting area. using the chair metaphor. Once you've determined 4 different carbons that make up this flat surface, then you can identify that one of these carbons, but due to the alternating pattern, is deflecting upwards. Here, this would be this carbon. And I would call this the headrest carbon. Alternatively, the other carbon is deflecting downwards, and I would refer to this as the footrest. So when we discuss the chair, we're not really talking about a dinner table chair or a stool. We're talking much more about a recliner. So if you're on the beach and you wanted to sit on this kind of chair, you would sit on this flat surface, put your head on the upward part and your feet on the downward part. And this kind of gives a better understanding of why we use this chair metaphor. And understanding the footrest and headrest carbon is going to be crucial in understanding the more complicated things to come in regards to chair drawing. Now, when it comes to drawing a chair, lots of students have difficulty, and this can be a very important skill to develop early, so I would recommend taking some time to practice. Let's go through a quick example of how I like to think about drawing a chair. Now first, I like to draw 2 slanted parallel lines, and importantly, you want to draw them pretty far apart. So I'd say further apart than they are long. If you draw the lines too close, your chair is going to look very constrained and not have the correct dimensions. So drawing 2 slanted parallel lines that are far apart. That's step 1. Now going to the second step. This one is a bit of a hard one here. But I like to draw 2 lines from the ends of one of the original lines that I drew. So what I'll do is I'll take these 2 ends of this line, and the goal will be to draw a line to the middle of the opposite line. Something like this. However, we're going to give up halfway. So we're going to draw this line and stop around the halfway point and do the same thing here. Now that I've done these 2 steps, the last step is simply to connect the dots. So we take these extra carbons that we've added in and we connect them to their respective carbons. And here we have something similar to a chair configuration. Now, the way that I drew this one, these carbons are perfectly overlapped. This isn't horrible, but later when we start drawing the substituents on the chair, that's going to make this area a bit of a mess. So I would advise that you try to make these a little bit offset. Making one of these lines a little bit shorter can help later on when drawing the substituents on that chair. But now that we have our chair configuration drawing, let's talk about how we can add the remaining substituents on this carbon and how we can relate it to the flat projection that we discussed earlier. Comparing the chair configuration and the flat projection are going to be very important skills in this unit. So I'll see you in the next lecture to discuss the axial and equatorial substituents of the chair.